Greetings. We're making a supplemental video here. This is going along with chapter 4 in your book on number theory. Just give me a moment here. I'm not quite set up. There we go. Okay. So this is a supplemental video, and what we're concerned with here, related things. First of all, we've already discussed this before, but we're going to be doing it again. Finding the greatest common divisor. In other words, if we're given two integers, suppose we're given the number 48, and we are also given the number, let's say 104, and we want to find the greatest common divisor of these two numbers. Well, that's defined to be some integer n such that n divides 48 and n also divides 104. And if there are any other integers that divide 48 and 94, in other words, if there's an m that divides 48 and there's also an m that divides 104, then m is less than or equal to n. In other words, n is the greatest number that divides both of these. And there are several ways to find this, and this is very important. I'm assuming that most people taking this class plan on ultimately taking a class in cryptography, and this notion of a greatest common divisor is very important in a cryptography class. Now, we said that the first way that you could do this is you could factor 48 and 104 into its unique prime factorization. So we know if I'm given the number 48, well, 48 is 2 times 24, and 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. So I've got 1, 2, 3, 4 2's. So this is equal to 2 to the 4th times 3. And that is the unique prime factorization, I should say 3 to the 1st. That is the unique prime factorization of 48. If I come over here and I want to do the same thing for 104, well, 104 is 2 times, let's see, that would be 52. And 52 is 2 times 26. And 26 is 2 times 13. So this is equal to, let's see, that's 2 to the 1st, 2 to the 2nd, 2 to the 3rd, times 13. So if I'm looking for the GCD of 48 and 104, well, I note a couple of things. When I look at the prime factorization, well, they both contain 2's. And now what I have to do is I have to look for the smaller exponent. Okay, I hope that makes sense to you. The bigger exponent, of course, 2 to the 4th would divide this number, but 2 to the 4th wouldn't divide this number. So I want 2 to the 3rd. We see that 48 has a 3 in it, but 104 doesn't have a 3 in it. We see that 104 has a 13 in it, but 48 doesn't. So we're done. So the GCD of 48 and 104 is just the number 8. I hope that was pretty clear. One more thing that I want to note here, maybe we should go ahead and do another example. Suppose I'm asked to find the GCD of 15 and let's say 64. Now, 15 is equal to 3 to the first times 5 to the first. And 64, let's see, 64, 2 times 2 is 4 times 2 is 8, 16, 32, 64, 1, 2, 3, 4, 5, 6 is equal to 2 to the sixth. So we can see over here, they have no prime numbers in common. We have just 2's for 64, for 15 we have 3 and 5. So the GCD of 15 and 64 is equal to 1. Okay? 1 is the biggest integer that divides both of these numbers. And in a situation where we have the number 1 being the greatest common divisor, we would say that 15 and 64 are relatively prime. And that's an important definition. We will call on that again. So that ends our first method for finding the greatest common divisor. Okay, so what we would like to do now, we're going to be learning this thing called the Euclidean algorithm, named after Mr. Euclid. Famous guy from Greece. And again, I want to go back to the problem of find the GCD of 48 and 104. This was the same problem that we had before. Now, before I proceed on this one, I want to recall a fact that we learned earlier in this chapter, namely that if I have that A divides B and A divides C, then A divides B minus C. Okay, and if you don't remember that, then it would be a nice exercise for you right now to go ahead and prove this. Incidentally, it would also be the case that A would divide B plus C. But the reason why I bring that up is that is really the key to the Euclidean algorithm. And I'm going to come over here and I'm going to say that the GCD of 48 and 104 is actually equal to, and what I'm going to do here is I'm going to go, well, 104 is the bigger number. So what I'm going to do is I'm going to say that's equal to the GCD of 48 and 104 minus 48. Now notice the 104 minus 48 is this B minus C over here. So that if I come over here and I do this subtraction, that's equal to the GCD of 48. And let's see, I've got to do this in my head. 104 minus 48 is going to be 6. Is that going to be 56? I hope I have that right. 104, 48, that's going to be a 9, and 14 take away is 6, and that's 56. So that's equal to this. Okay, the original problem, GCD of 48 and 104, well, that's equal to the GCD of 48 and 56. Well, I'm going to continue this process. The GCD of 48 and 56 is equal to the GCD. And what I'm going to do is again, I'm going to subtract the smaller one from the larger one. So that's going to be 48, comma, and it's going to be 56 minus 48. And that's equal to the GCD of 48. And I think I can do this one in my head. That's going to be 8. And I'm going to do this again. This time I'm going to subtract in the other direction because this is the bigger one. So that's going to be the GCD of 48 minus 8, comma 8 is equal to the GCD of 40 and 8. And I think you can see what's going to happen again. That's equal to, I'm going to skip some steps here now because I think you're starting to see the pattern. That's equal to the GCD. I'm going to go 40 minus 8. That's going to be 32, 8. And that's equal to the GCD of, and I'm going to go 32 minus 8. That's 24, 8. And that's equal to the GCD. And I'm going to go 24 minus 8. That's 16, 8. And I'm going to subtract 8 from 16 again, and I get the GCD of 8, comma 8. And I think one thing that should be clear at this point is that whenever I'm taking the greatest common divisor of two numbers that are exactly the same, it's just that number. So I get this number right over here. Okay, the GCD, so the original problem, the GCD of 48 and 104 is equal to the GCD of 8, comma 8, and that's equal to 8. So one of the things you need to remember here is that the GCD of any A, comma A is just equal to A. The other fact that you're going to need to keep in mind here is that the GCD of A and 1 is equal to the GCD of 1 and A, and that's just equal to 1. And I think you can see that if I were to have the GCD of A, comma 1, then that's going to be equal to, and remember I could subtract, that would be equal to the GCD of A minus 1, comma 1, and we would keep subtracting until it just got down to the GCD of 1, comma 1. Let's consider one more example. Let's find the GCD of 8, and let's think of another good example here. What about 15? Well, that's going to be equal to the GCD of 8 and 15 minus 8, which is equal to the GCD of 8 and 7, which is equal to the GCD of 8 minus 7, 7, which is equal to the GCD of 1, comma 7, and we can see that that's going to be 1, okay? And our conclusion here would be that 8 and 15 are relatively prime. Which I don't think is a surprise to anybody. Okay, good. So this is what's called the Euclidean algorithm. Finally, the last thing that we need to talk about here, and this is really the most important of all these things for finding the GCD, is what's called the extended Euclidean algorithm. And this is very important for cryptography, so it's important that you understand this. And let's see, let's try and find a good example. I had one worked out here. I seem to have misplaced it. Suppose we are asked to find the GCD of 240, I hope this works out nicely, and 63. Okay, now let's suppose that this GCD is equal to some number G. And we don't know what G is, but let's suppose that we have it already. The extended Euclidean algorithm not only finds this number G, but it does something a little bit more. It says that G is equal to 240 times A plus 63 times B, and it finds A and B. Okay, in other words, what the actual extended Euclidean algorithm is telling us is it's telling us that the greatest common divisor is somehow a combination of 240 and 63. In fact, one thing that you could get is if you were to let A and B range over all the values of integers, this is going to generate a whole bunch of different numbers. The smallest positive integer that it generates is the greatest common divisor. Now, this all may sound very confusing right now. We're going to work through some examples here, and later on we're going to see that finding these numbers is very, very important. But the idea here is actually very simple. Notice I'm trying to find the greatest common divisor. One number is bigger than the other. What I'm going to do over here is I'm going to do some very simple division here, and I'm going to say that, well, the number 63 goes into the number 240 times. Well, it goes in there 3 times, and I get 9, 1, 8, and when I go ahead and I subtract, I get 51. So there's a remainder here of 51. Or to state it another way, 240 is equal to 3 times 63 plus 51. Okay? So that's step number 1. The next thing I'm going to do is I'm actually going to repeat this whole process again, but instead of with 240 and 63, I want to repeat the process with 63 and 51. In other words, I'm going to come over here and I'm going to go, well, 51 goes into 63. It goes in there 1 time, and it's got a remainder of 12. So that says to me that 63 is equal to 1 times 51 plus 12. And now what I want to do is I want to repeat this process again, but this time with 51 and 12. And I go, well, 12 goes into 51 4 times, and I've got a remainder of 3. So I'm going to come over here and I'm going to say that 51 is equal to 4 times 12 plus 3. And finally what I'm going to do is I'm going to do this with 12 and 3. And I say, well, 3 goes into 12 4 times, remainder 0. And that actually tells me something very, very, very important. This thing right over here tells me that this is the GCD. So in this case over here, the GCD is 3. Okay? Once I go ahead and do one of these divisions and I get a remainder of 0, the divisor there is clearly the remainder. Okay? So now we have the question, how do I find A and B? And the answer here is that I basically work backwards. Okay? This statement over here, this last statement here, tells me that 3 is equal to 51 minus 4 times 12. Okay? Now I'm going to come over here And I am going to solve this statement over here for 12, and that tells me that 12 is equal to 63 minus 1 times 51. Well, what I'm going to do is I'm going to take this expression for 12 here, and I'm going to substitute it back in here. So that tells me that 3 is actually equal to 51 minus 4 times, and now I'm going to put in that expression for 12, 63 minus 1 times 51. Okay, and let's do a little simplification here. So that tells me that 3 is equal to 51 minus, I've got 4 times 63, and then I've got plus 4 times 51. So that says to me that 3, I've got a 51 here, and I've got 4 51s here. That's 5 times 51 minus 4 times 63. Now I am almost done. I'm going to come over here in this expression here, and notice that I can solve for 51. So let me see if I can do this and keep everything up on the screen for you. I'm going to move this over a little bit. And I'm going to come over here, and we'll try and open up a new, and I'll say OK. And we're going to move this over to here. So let's see what information we have and what information we need. So I'm going to look at this expression over here, and this expression over here says to me that 51 is equal to 240 minus 3 times 63. That's what I got over here. And what I have over here, I'm just rewriting this now so that we can see everything. I have that 3 is equal to 5 times 51, okay, minus 4 times 63. So what I'm going to do is I'm going to substitute this expression for 51 in here, and I get that 3 is equal to 5 times, and this is going to be 240, minus 3 times 63, and then I have minus 4 times 63. And we're almost done. We just need to simplify everything. So 3 is equal to, I've got 5 times 240. Over here, I'm going to get 5 times a minus 3. That's minus 15 times 63. And over here, I've got minus 4 times 63. And that says to me that 3 is equal to 5 times 240 minus, let's see, I've got minus 15 times 63. I've got minus 4 times 63. That's minus 19 times 63. So we've done a couple of things over here. First of all, we have found the greatest common divisor. And remember what our goal was. I'm going to come back over to this slide for a second. Our goal was to find the numbers a and b such that 240 times a plus 63 times b, okay, would give us the greatest common divisor. And we found those numbers right over here. It turns over that this would be the number a would be 5, and b would be minus 19. Now, it may not be clear to you, in fact, I'm sure it's not clear to you why this is important, but we'll do another example and then I will demonstrate why it's important. Okay, let's do one more example just for practice here. Suppose I'm asked to find the GCD of 54 and 96. And that's equal to some number g that is equal to 54a plus 96b, and we have to find a and b. So the way we go ahead and do this is, first of all, we go 54 goes into 96 one time, 54, and I get a 2, and I get a 42. So I get that 96, I'm going to write it way over here. 96 is equal to 1 times 54 plus 42. Then what I'm going to do is I'm going to go, well, 42 goes into 54 one time, 42, with a remainder of 12. So I'm going to come over here. Remember, what I have over here is a remainder of 42. Over here I have a remainder of 12. So I'm going to come over here and I'm going to say that 42 is equal to, nope, that's the wrong thing to write there. I'm going to say that 54 is equal to 1 times 42 plus 12. And now I'm going to go 12 goes into 42. 3 times 36 with a remainder of 6. So there's a remainder of 6 here. So I get that 42 is equal to 3 times 12 plus 6. And then what happens over here is I get that 6 goes into 12 2 times with a remainder of 0. And that tells me that this is my GCD right over here. So G is equal to 6. The greatest common divisor of 54 and 96 is 6. Now I want to find the numbers A and B. And I come over here, and this tells me, this last line right here says to me, I'm going to write it, move it over here, because I know I'm going to need room, that 6 is equal to 42 minus 3 times 12. And I come up to this line right here, and this tells me that 12 is equal to 54 minus 1 times 42. So I'm going to take this expression for 12 and put it in here, and I get that 6 is equal to 42 minus 3 times 54 minus 1 times 42. And I'm going to go ahead and collect terms here. So that's 42 minus 3 times 54. And over here, minus 3 times, minus 1, that's going to be plus 3 times 42. And again, I'm going to collect terms here. I've got 42 and 3 times 42, that's 4 times 42. And over here, it looks like I have minus 3 times 54. Okay, so we'll keep this expression in mind. I'm going to come over here, and I look at this, and I'm going to solve for 42. So I get that 42 is equal to 96 minus 1 times 54. And I'm going to take this expression for 42, and I'm going to put it over there. So I get that 6 is equal to 4 times 42, 4 times, and now I substitute 96 minus 1 times 54. Okay, minus 3 times 54. And that is equal to 4 times 96. And I've got minus 4 times 54. And then I've got minus 3 times 54. And that is equal to 4 times 96. And I've got a minus 4 times 54 and a minus 3 times 54. That's minus 7 times 54. So getting back over here, if I'm looking for the number A, we can see that the number A here would be minus 7. And if I'm looking for the number B, we could see that the number B here would be 4. And you should substitute these two numbers into here and see that it satisfies the equation. Okay, let's put this all together and see where this may be useful for us sometime in the future. Suppose I were asked the following question. Suppose I were to ask to solve five times x is congruent to 1 mod 7. Okay, so what we're doing here is we're asking for an integer x that I can multiply by 5 such that if I subtract 1 from it, it's divisible by 7. Stated another way, find x such that 5x minus 1 is divisible by 7. I hope that's clear. One of the things that we should note, at least when it's written this way, the assumption is that x is contained in the set. It would be 0, 1, 2, 3, 4, 5, 6. Okay? When we're dealing with the integers mod 7, remember, we're only dealing with the integers 0 through 6. These all correspond to remainders. Now, an easy way to do this is we could just try stuff. We could go over here, well, 5 times 0, that's congruent to 0 mod 7. And we could go that 5 times 1, well, that's congruent to 1 mod 7. 5 times 2, well, that's equal to 10. And 10 mod 7 is equal to 3 mod 7. 5 times 3 is equal to 15, and when we divide that by 7, 1 mod 7. So we found the answer right here. The answer is 3, but I want to develop a theory here where we could solve problems like this when the numbers are much bigger. Now, the first thing to note over here when I'm asked to solve this, the thing to note is that the GCD of 5 and 7 is equal to 1. We know that very simply because 7 is a prime number, 5 is less than 7. There can't be a number other than 1 that would divide both of them. So this is the case. What we've also learned previously is we know then that 1 is equal to 7 times A plus 5 times B, and we just need to find the A and B that will make this a true statement. Well, we know we can do that with the Euclidean algorithm. But here's the thing that I want you to note. If I just transpose this around, this is the same thing as saying 7 times A minus A is equal to 5B minus 1. Well, remember, minus A is just another integer, so we see that 7 clearly divides this side, which implies that 7 divides this side. And we can see that the number B that we find here actually corresponds to the x that we're looking for right over here. Very neat, isn't it? Well, we know the following. I hope I can take some shortcuts with you now. If I divide 5 into 7, we know that 7 is equal to 1 times 5 plus 2. Okay, and now I'm going to divide 2 into 5, and I get that 5 is equal to 2 times 2 plus 1. Okay, I know that 1 goes into 2 times, so I'm all done. So this is clearly the greatest common divisor. And if I come over here, I get that 1 is equal to 5 minus 2 times 2. And now if I come over here, this tells me that 7 minus 1 times 5 is equal to 2. So I'll substitute that expression in here, and I get 1 is equal to 5 minus 2 times 7 minus 1 times 5. And that tells me that 1 is equal to 5 minus 2 times 7, and minus 2 times a minus 1 is a plus 2. And that is equal to, let's see, 5 plus 2 times 5 is 3 times 5 minus 2 times 7. And we can see that we got the number 3 here that corresponds to the number 3 here. And we can see that we have solved that. Let's try a more complicated example, just to show you the power of this. So suppose, let me get a clean screen here, and I say, okay, there's our clean screen. Find the greatest common divisor, or no, not the greatest common divisor. I'm going to say over here, solve for x, and I'll come over here and I'll say something like 28x is equivalent to 1 mod 59. Okay, now the reason I chose this is the following reason. 59 is a prime number, so I know right away that the GCD of 28 and 59, I know that that's equal to 1. So I know that there exist integers a and b such that 28a plus 59b is equal to 1. This should be a 59. And I know that x would correspond to whatever this a is. So I just need to find it. So I'm going to go, this may be a little bit easier than I realized. 28 goes into 59. Well, if I go, no, this will be a little bit of work. I come in here and that's 2, and that's 56, and that leaves me a 3. So I get that 59 is equal to 2 times 28 plus 3. And now I'm going to divide 3 into 28, and 3 goes into 28 9 times with a remainder of 1. So now I have that 28 is equal to 3 times 9 plus 1. I'm all done. 1 is the GCD. So 1 is equal to 28 minus 3 times 9. And over here, I'm going to solve for 3. I get that 59 minus 2 times 28 is equal to 3. So I'm going to take this expression over here for 3 and substitute it in there, and I get that 1 is equal to 28 minus, I'm going to flip these two numbers around. I'm going to say minus 9 times 59 minus 2 times 28, and that is equal to 28 minus 9 times 59 plus 18 times 28. So I get that 1 is equal to minus 9 times 59. And now I've got a 28 here, and I've got 18 28, so that's plus 19 times 28. So that says to me that the solution for this would be x is equal to 19. We can prove it. I'm going to come over here and I'm going to go 28 times 19. That's 72. Carry the 7. 9 times 2 is 18 plus 7 is 25. I'm going to come over here and I have 28. So that gives me 2, and that's a 3. Carry the 1. That's 532. Now what I need to do is I need to divide 59 into 532. And that looks like it goes in there, I can't tell, 8 times, 9 times. Well, this is almost 60. Let's see if I do a 9. 9 times 9 is 81. Carry the 8. 9 times 5 is 45, plus 8 is 53. Yep, that does it. 53 with a remainder of 1. which is exactly what we got over here. Okay? So we proved it. Okay, I hope that's clear. If it isn't, it will become clearer by doing some exercises, and I am going to assign a whole bunch of exercises here. This is really important. What we've done here in this chapter, and especially in this last video here, is very important for the class in cryptography. Okay, good luck.